we'll talk about free modules today. So this is and for us we'll only be talking about free modules of finite rank or finitely generated free modules. These are the ones which resemble finite dimensional vector spaces, but they are just over arbitrary rings. So the definitions are all very familiar. So this should look like vector spaces. So suppose I take a ring R, not necessarily commutative, it can be anything. What's the free module? So let's define this to be R to the n. So the free module any such thing is called a free module. Okay, what does it look like? Looks like R to the n, which is all n tuples. So this is all elements of the form a1, a2, an, where ai's come from the ring R. Okay, and we think of this as an R module. Okay, what's the R module structure? Well, we do component wise addition and component wise scalar multiplication. So this becomes a left R module under the component wise operations. Component wise addition and scalar multiplication. Okay, and this is of course since we have talked about direct sums and so on, as you can see, this is actually nothing but another way of saying look at just R thought of as a module over itself, and this is just isomorphic to the direct sum of R with itself n times. Okay, you take n copies of the ring R thought of as a module over itself, and that direct sum is exactly what we are thinking of in this way. Okay, and of course these share a lot of properties with vector spaces over a field or with n-dimensional vector spaces, but there are also some important differences. Okay, so we need to sort of be a little wary of these. So let's look at the standard basis in some sense. So let's define the element ei, which is 0 everywhere else except 1 in the ith position. So this is the ith place, zeros. Okay, so we define this as ei, I goes from 1 to n, and as is clear, every element of the ring R, because the operations are component wise, if I give any element of this module, if I take an element x in Rn, then this element can be uniquely written. So every element x in Rn can be uniquely expressed as a linear combination of these ei's, summation ci ei. This is more or less from definition, where the ci's come from the ring R. Okay, so that's like vector spaces again, and the key point is free modules are especially good when you are trying to define homomorphisms from it to other modules. So how do you define homomorphisms from a free module? So suppose I give you a free module Rn and I want to define a homomorphism to any other R module M. Okay, I want a homomorphism. The way to define it is just by stipulating its values on a basis. Okay, so a homomorphism is uniquely determined by its values on a basis. So a homomorphism phi to any module M is uniquely determined once you tell me what the basis elements go to by the values phi of ei. And why is that? Because once you know it on the basis, on any other element you will just use the fact that that element can be written as summation ci ei, and therefore the property of homomorphism says I can pull all the ci's out, write it as a linear combination. So this is just by the definition of a homomorphism, and since I have stipulated these values, there are some elements of M, summation ci times those elements is some well defined element of n. Okay, so this is how you would define the homomorphism. Okay, so this is also well defined. So this is like if I pick arbitrary, so okay, so there is actually a existence and uniqueness statement that's hidden in this, which is that if you give me some elements mi, then I can find a homomorphism such that phi ei is mi, and there is only a unique such homomorphism. Okay, so maybe one should just make this slightly more precise. So let me just make the precise statement, and you can just prove it from what I just said. So here's the statement: given mi's in M, there exists a unique homomorphism phi from Rn to M, which maps ei to mi. Okay, so this is really the key statement. This is the statement I am trying to make. Okay, and the proof is more or less obvious. Okay, so this is how you define homomorphisms from Rn, and so it's sort of interesting to study homomorphisms from Rn to another free module Rm. Okay, so by the same token, suppose I wanted to understand what homomorphisms from Rn to Rm look like. So what am I supposed to do to specify this homomorphism? What I should do is, for each ei, I should give you some element mi, okay, in this module Rm. Okay, now what does Rm look like? Well, there are too many m's, so maybe I will just give this some other name. Let me call it xi. So I need to specify an element xi in Rm, but Rm, remember, itself is again a free module. So any element of Rm can be uniquely written as a linear combination of its basis elements, right? So let me give the basis elements of Rm a name. Let me call them fj's now. So what is fj? This is 0 0 0 1 in the jth place. Okay, 0 0 0. So I am thinking of it as an element of the free module Rm. Okay, so observe that f1, f2, fm will form a sort of a basis for Rm, if you wish. Okay, so each xi, since it's in Rm, it can be uniquely written as a linear combination of the fj's. Okay, so let's do that. Let's write xi as some linear combination, and now I will use aij's to denote the linear combination, the elements of R which occur in the linear combination. So this is now the sum, j goes from 1 to m. Okay, and what are the aij's? They are some elements of R. So what are aij's? Okay, so our previous discussion then says that to specify a homomorphism from Rn to Rm, you just need to tell me what are all these xi's, these n xi's, or equivalently, you just need to tell me what these scalars aij are. Now here, how many of them are there? I is from 1 to n, j is from 1 to m, and the appropriate way to arrange this is in the form of a matrix, okay, just like we do for vector spaces. So a homomorphism phi is uniquely determined by a matrix. So I want to say, let's take an m cross n matrix. This is like in the convention for vector spaces. So this is an m cross n matrix. So to be very precise, I mean, for it to match our usual conventions, what I should do is to change these i's and j's around. So let me just do one little thing here so that it matches with vector spaces. So let me say, let me take ej. So j will go from 1 to n. So I am going to switch the roles of I and j here. So ej maps to xj. Okay, now I, which is this other variable now, will go from 1 to m. Okay, so I goes from 1 to m, and observe that what I am doing here is what we do for vector spaces, which is that we put these scalars along the columns. Okay, so what does this mean? So what have I done? I am saying ej maps to xj. xj is summation aij fi. Okay, so in other words, if I wanted to know what is phi acting on ej, then the scalars which occur are in the jth column of A. Okay. So, this is our usual convention, arrange along the columns rather than along the rows. Okay. So, I hope that definition is clear there. So, I just need to tell you what these scalars are. These I need to tell you this M cross N matrix Aij. Now, let's sort of look at one little difference. Now, so far it's looking a lot like vector spaces, but there is one little twist to the tail. So, let's just see. Suppose I give you this matrix. So, given this matrix A, given A. So, what is A now? It is an element of, so let me use this notation, matrices M cross N whose entries are not in a field necessarily, but in the ring R. So, given a matrix A, M cross N with entries in R, we define the homomorphism phi as before using this matrix by saying that the value on Ej is the scalars in the jth column. So, Aij Fi, I goes from 1 to n. Okay, and this is for all j between 1 and n. So, if we do this, then what does the value become on a general element? Okay, so suppose I pick on a general element of x in Rn. So, what does that mean? I can write this element x as some linear combination xj ej. Okay. On a general element, how does phi act? Let us compute phi acting on x. Now, we have to be very careful when we do this. So, phi acting on summation xj ej by definition is, I can pull the xj's out, j goes from 1 to n, xj phi ej, okay, and phi ej, remember, is what is written on top. So, there is a double summation here, but since R is not a commutative ring, I have to be careful with the order in which I multiply my scalars. Okay, so phi of Ej, I am just going to use this equation on top, which says this is summation I goes from 1 to m. This is xj times Aij times Fi. Okay, and I can switch the order of summation here. I can think of it as summing first over I, then over j. That's fine. I'm just doing the same sum in a different order. So, this is summation I goes from 1 to m, summation j goes from 1 to n now, and what I have here is xj Aij, okay, times Fi. Okay, so this is my final formula. So, observe, so I'm sort of doing this slowly to point out that, you know, in the case of vector spaces you still get the same formula, but the ring there is a field, okay, which is commutative. So, these in the case of vector spaces we would tend to write this formula as summation Aij xj rather than summation xj Aij. But in this case you are not allowed to commute these two things. The x has to come before the entries of A. Okay. So, this is the key point to note here, that we are used to writing it in the other order for vector spaces because they commute, but when you are trying to do this for general rings we have to be a little careful. Okay, so anyway, that's the formula here. Now, observe, this is so we should really think of this as well, if we were able to commute these two guys, you would write this as the product of the matrix A with the column vector x, and this is the ith element in that product. In this case you can't quite do that. Okay, so let's just look at one more such case where it will become clearer. So, if I take for example Rn, Rm, Rp, so I take 3 such free modules and I sort of do a similar thing. I take a basis of this free module, call it Ek, this free module, call it Fj, let's call these Vi's, Okay, so this is now k going from 1 to n, j going from 1 to m, and I going from 1 to p. Okay, so I take three bases, and now I have two homomorphisms phi and psi. Each homomorphism is determined by the knowledge of an appropriate matrix, right? So suppose I call those two matrices which determine this homomorphism and this homomorphism, let's call the corresponding matrices A and B. Okay, A will be whatever m cross n and B will be p cross m, right? So this is m cross n and this is going to be p cross m. So I have two matrices, and now if I compute what the matrix of their composition is, okay, this is again something which we are used to do in the case of vector spaces. So if you compute psi composition phi, and I need to figure out what the matrix of the composition looks like, which means I should just figure out what this composition does to the basis vectors ek, right, to these elements ek. So I need to compute the value on ek. So let's just do that. That is just psi evaluated on phi of ek. Okay, now I'm given that this matrix is A. That means I know what phi of ek is. This is just psi of summation A, let's call this jk fj. Now j is being summed over 1 to m. Now when I apply psi to this, what am I supposed to do? I pull the A out, j goes from 1 to m, this becomes A jk, and I need to evaluate psi of fj. Okay, so this is psi of fj, and in the last step, what am I supposed to do? Psi of fj has to be replaced by whatever it's equal to, right? So let me just do it right there. So let me erase this. Psi of fj is summation, it's given by the matrix B, summation I from so this is Bij ei. Okay, so I've just used the definition of psi of fj and the matrix B. Okay, so now you'll already start seeing a problem. So I just changed the order of summation. This I goes from 1 to p, and inside is summation j equals 1 to m A jk Bij times ei. Okay, and now we are done. That's the end of the computation, because I'm trying to find out what is the composed map acting on ek. Sorry, these should have been v's here. So this should have been vi. It's an element of Rp. So now the composed map is again given by a matrix, right? The entries of that matrix are exactly what I get when I write psi composition phi ek as a linear combination of the vi's. But now these therefore are the entries of that matrix. Okay, so what this means is that psi composition phi, suppose this is given by a matrix C, okay, and this is now a p cross n matrix, right? P cross n would be this full composition here. Okay, now in the case of if you remember how things work in the case of vector spaces, we would just say, oh, that matrix C is known, it's just a product of the two matrices B and A, right? This is how it works when you compute matrices of linear transformations in the case of vector spaces. But now observe that our answer isn't quite that, because A and B, I mean it's looking like that. If the ring were commutative, then of course you could change the order of B and A and rewrite this term here as Bij Ajk sum over j, okay, and then it would exactly be the product of B and A. Okay, now the trouble is here, things don't commute. So this matrix C that you have, the elements of this matrix are the following: Cik, the kth column, ith entry is the sum j going from 1 to n, okay, and it's almost what you would expect. In the case of vector spaces, you would have expected the following: it's B times A, so you would have written Bij times Ajk. This is what you would have wanted to write in the case of vector spaces. but in this case it doesn't occur like that, it occurs in the other order. Okay, so which means that this A actually occurs on the other side, so I need to push this A over to the other side. Okay, so that's the form of the answer here. Okay, so let's just erase this, make it slightly neater. So this is AJK Bij, and that sort of seems rather unfortunate that we can't quite think of it the same way as vector spaces, but what we do is something rather interesting here. Recall that we talked about something called the opposite ring of a ring R. Okay, so recall I once talked about something called R op. What is this? It's the same ring, it's the same set R with the same addition, but the multiplication alone is different. So what's the new multiplication in the opposite ring? If I have to multiply two elements A and B, I just take the usual multiplication in the ring but in the opposite order. Okay, so given a ring, there is this opposite ring in which the multiplication is just the product in the other order. And so what we can do now is to think of this as, instead of AJK Bij, well, I'll do the following. I'll think of it as, well, it's just Bij into AJK, except that this product is taken in the opposite ring. Okay, so now I'm going to take the opposite product. Okay, so now that's already nicer. It brings things into the same setup as vector spaces. The matrix C is actually the product B times A, but we should just take care to use not the usual ring multiplication but the multiplication in the opposite ring. Okay, so what we have really shown so far is the following statement, that if you want to look at module homomorphisms from Rn to Rm, then the sort of the correct formulation, the correct way to think of it is the following: each homomorphism gives rise to a matrix. Okay, so this gives rise to an M cross N matrix, and the elements are, well, they are elements of R of course, but the correct way to think about it is that they are elements of R op. So if you think of each homomorphism as giving you a matrix, M cross N matrix with entries in R op, then the composition takes on this rather nice thing, which is that if I compose two such homomorphisms from Rn, Rm, Rp, so this is phi and psi, then as we just saw, if the matrix of the first guy is an A, this is an A and this matrix is B, then the matrix of psi phi will just turn out to be, so this matrix will turn out to be BA, but remembering that the elements are A's and B's, the elements of A and B are elements of R op and not elements of R. Okay, and in fact this is we can also do the special case when n equals m. So this is, so recall we call these the space of endomorphisms. So if I just take n equals m, then end of Rn just means all module homomorphisms from Rn to itself. Okay, and now this is every such homomorphism. To every such homomorphism we can associate an n cross n matrix. So let me just say mat n, meaning n cross n matrix, whose elements are in R op. Okay, so this is called the matrix of this homomorphism. And now the beauty is that the space end Rn is it's actually a ring. Okay, so here's a little exercise. Observe that end Rn is a ring under composition of maps. So this is a ring under pointwise addition and composition. So addition is pointwise addition and the multiplication is the composition of maps. Okay. On the other hand, mat, the space of matrices with with entries in a ring R, is also a ring. Okay, under the usual matrix addition and matrix multiplication. So observe that the right hand side is also a ring. Mat n entries in any ring is a ring under matrix addition and matrix multiplication, and check that this association, so here's the exercise, check that phi going to matrix of phi is actually a ring homomorphism. Okay, so we actually checked some bits of this, which is, I mean, the only thing really to check is that the multiplication is respected on the two sides, but that was really the point that we spent a lot of time over, which is that when I take two homomorphisms phi and psi, the composition of psi and phi goes to the product of the two matrices, except that I should think that the entries come from R op and not from R. Okay. And recall also that we have sort of seen an instance of this before in one of the problem sessions, which is that if I take n equals 1, which means I just think of R as a module over itself, okay, and I ask what are all the endomorphisms of R, right, which means what are all the homomorphisms of R, I mean homomorphisms from R to R, then we sort of had done this before, that this is actually isomorphic to the ring R op. Okay, and what was the map? Each homomorphism looks like a sort of a right multiplication. Okay, so each homomorphism phi here, so what are the homomorphisms? Well, maybe I should say the map in the opposite direction is what we looked at. Given any element of R or R op, it induces a homomorphism here phi sub b as follows: phi sub b acting on x is xb, the right multiplication by b map. Okay, and that's exactly this. I mean, this is the thing we are looking at here is a generalization of that to arbitrary values of n. Okay, okay.